When evaluating an algorithm, the true test isn't processing 10 or 100 items. It is how the system behaves as data accelerates toward infinity. This visualization plots the execution time of two theoretical models. On the left, a linear algorithm scales in direct proportion to the data. On the right, a quadratic algorithm executes at the square of the input, creating an aggressive upward spike. Attempting to measure these execution times in exact milliseconds is a flawed approach. A poorly designed algorithm running on a modern, high-speed processor might execute a small dataset faster than a highly optimized algorithm on older hardware. The physical hardware obscures the actual code efficiency. To accurately determine which algorithm will survive at a massive scale, we have to strip away processor speed entirely. Mathematical growth trajectory is the only viable metric. Big O notation is the standardized mathematical framework used to evaluate this exact growth trajectory. Its core function is to describe the structural ceiling of an algorithm. We call this the upper bound, the absolute maximum rate at which an algorithm's time can increase. If an algorithm happens to encounter perfect data and finishes instantly, Big O ignores it. The framework specifically evaluates the worst-case scenario for execution time, regardless of optimal inputs. By isolating this worst-case scenario, Big O provides a strict mathematical guarantee. It ensures that an algorithm's performance will never degrade beyond its stated structural ceiling. Establishing this ceiling requires moving from a conceptual bound to a strict algebraic definition. An algorithm's exact time complexity, f of n, belongs to a specific Big O classification only if it meets precise mathematical conditions. This graph maps the core inequality formula. The actual running time, f of n, must be less than or equal to a constant c multiplied by a reference growth rate, g of n. The constant multiplier c scales the theoretical bound. By adjusting c, we ensure the reference curve eclipses the actual time curve entirely. Because we are only concerned with scalability, this rule does not need to apply to microscopic inputs. We establish a starting point, n0. This marks the exact input size where the theoretical upper bound permanently overtakes the actual running time. If we can successfully calculate and prove the existence of these two positive constants, c and n0, the Big O bound is officially verified. Here is the algebraic equation for an algorithm with a running time of 3n plus 5. Our objective is to prove that this acyclic function belongs to O of n. We establish our condition: the input size n must be greater than or equal to 5. By setting this boundary, we can legally substitute the integer 5 with the variable n. This transforms our expression into the inequality 3n plus 5 is less than or equal to 3n plus n. We combine those terms on the right to reveal 4n. This isolates our constant multiplier as c equals 4. The first proof is complete. We apply the same logic to a more complex layout. The quadratic polynomial 4n squared plus 3n plus 2. We need to establish that this equals O of n squared. We inflate the lower order variables to match the highest power. By establishing a starting point where n is greater than or equal to 1, we scale 3n and 2 directly into 3n squared and 2n squared. Combining all the quadratic terms together yields 9n squared. Our constant multiplier is isolated, c equals 9. Through rigorous algebraic substitution, we derive an objective, mathematically sound method to prove algorithmic bounds. Physical hardware testing is unnecessary. Writing manual algebraic proofs for every code snippet is highly inefficient. Instead, we extract 3 practical rules of abstraction to evaluate algorithms on site. Rule 1, remove flat constants. Rule 2, keep the highest power. Rule 3, discard lower-order variables. An algorithm executing 100n steps evaluates exactly like 5n steps. The flat numbers drop away. And a complex time like n cubed plus n squared plus n distills simply to O of n cubed. As the input size approaches infinity, the lower order terms and flat numerical constants lose their gravitational pull on the output. The highest growing polynomial term entirely dictates the behavior of the curve at infinite scale. Every other variable is structurally insignificant. These mathematical growth rules map directly onto programming constructs. A basic isolated execution statement creates a baseline bound of O of 1, constant time. A single loop stepping systematically through an entire dataset yields O of n linear time. Nested loops naturally multiply these iterations. A loop running n times inside another loop running n times yields the standard O of n squared quadratic complexity. The triangular nested loop presents a specific edge case. Here, the inner loop's execution limit is strictly dependent on the outer loop. This visual cascade represents the exact operation count of a triangular loop. Instead of an n by n grid, the sequence of executions follows the arithmetic series formula, n times n plus 1 divided by 2. We expand the formula into n squared plus n over 2. Applying our abstraction rules, we immediately strip away the division constant, and we discard the lower order n. We are left with a single dominant n squared. A triangular loop executes exactly half as many total operations as a standard nested loop, yet its scaling behavior remains strictly an O(n) squared algorithm at massive scale. This macroscopic table ranks the complete hierarchy of big O complexities. We can map algorithms directly to their structural limits, from the most optimal to the least optimal growth rates. Highly efficient logarithmic algorithms, like binary search operating at O of log n, sit at the optimal end of this spectrum, scaling brilliantly against massive datasets. Standard sorting functions sit lower down the efficiency curve. Merge sort maxes out at O of n log n, while selection sort pushes further down, heavily constrained by its O(n) squared structure. Seemingly unique and intricate algorithms inevitably cluster into these rigid mathematical families of growth. Big O notation provides the absolute mathematical guarantee of an algorithm's worst-case structural ceiling. We derive the exact time equation, isolate the highest growing term, apply our rules of abstraction, and formalize the bound. But Big O contains a critical blind spot. It defines a strict ceiling, but offers zero information regarding an algorithm's best-case scenarios or minimum performance thresholds. To evaluate a system completely, we must lock in the opposite end of the spectrum. We have to map the absolute mathematical floor of an algorithm utilizing omega notation.